Oh, I know. As I shoved it in my bag as I walked. There it is. There it is. There it is. Calculus right there. There's my other calculus right there. Okay, so we're finding integrals from that integral handout sheet. And did we do number 9?
Yeah, we did.
Yeah. We did 9? Did we do 10? Yes or no?
No.
We did not do 10? That's a quickie. You recognize any function that you have encountered in your lives that has that thing right here as its derivative? It's an inverse something. Which one? Sorry? Not the sine. Arcsine and arcsecant have a square root. This one's the arctangent. Remember, we're looking for something that has this relationship. Whatever's inside the integral sign, called the integrand, has its antiderivative f plus an arbitrary constant, where the derivative of big F is equal to little f. So the derivative of arctangent is 1 over 1 plus x squared, and that makes the arctangent of x the antiderivative of that. Now, number 11, we got to do some steps before we can find the antiderivative. We don't have a quotient rule or a product rule. We just have a sum and difference rule. So I can't just go on the top and find the antiderivative of those two things, and then go on the bottom and find the antiderivative of the bottom thing. I've got to break this up so that it looks like stuff added together. We can find the integral of f plus g or f minus g term by term. And if there's a constant in there, we can always factor a constant out. So what we've got to do to this one is break this up first into two fractions. 1 over x to the 4th plus x squared over x to the 4th. So split the numerator. Then we've got to move those upstairs so they look like an x to a power. And then we can use our power rule. So I'm going to write 1 over x to the 4th as x to the negative 4. X squared over x to the 4th simplifies to 1 over x squared, but 1 over x squared can be written as x to the negative 2. And so now we're going to use our power rule. And in antiderivative, we undifferentiate. So instead of multiplying by the old exponent and then subtracting, we add first and then divide by the new exponent. So I add 1 to each power. So I get x to the negative 3 there on that first one. And then you divide by that new power. Add 1 to the negative 2, and I get x to the negative 1. And then I divide by that new power. That makes the antiderivative, so I tack on the general constant. Then we can put those x's back in the bottom and write that first fraction as 1 over 3x cubed and put the negative sign way out front. Same deal here. I put this negative sign right here and write that as 1 over x to the first. Oops, no more dx. That's a plus c. So we have sums, differences, and then we have a power rule, and then our antiderivative. So let's see if you recognize anything here on number 12. The 10 we don't have to worry about. We can pull the 10 out front. And then you got to think backwards. What did I take the derivative of to get 1 over the square root of 1 minus x squared? What did I just take the derivative of to get that? That one's the inverse sign. That one's the inverse sign. So our antiderivative is 10 times the arc sine of x plus our constant of integration. And number 13, I think it needs more room. Let me move 13 more to the middle of the board. I have a product of x minus 4 with 2x plus 1. Plus 1. And just like with this one, I have to make separate terms that are added or subtracted from one another. I can't just go inside of parentheses and find antiderivatives. I've got to make it a sum first. So we're going to have to multiply this out first. So I'm going to first multiply the 2x plus 1 by the x. And I have 2x squared plus x. And then I'm going to multiply the 2x plus 1 by the negative 4. And I get negative 8x minus 4. I guess I can go ahead and add the negative 8x with the x before I integrate. But I have some terms separated by the minus signs. Now we can just go through each term, add 1 to the power, and divide by the new power. We can pass over that 2 and that 7 and put them on at the end. So here's the 2, add 1 to the power, and I get x to the 3rd power, and then I divide by that. Okay, copy down to 7. Here our power is 1 when it's not written. So when I add 1 to the power, I get x squared, and then we divide by that. And what about the 4? What's the antiderivative of 4? 4x. And then we're done. All you do is multiply stuff out first. Okay. So now I want to show you where that c comes into play. See. Object has constant acceleration let's say it's moving on a number line. So let's say 5 units per minute. So it's units per minute squared. Find the position of this object at time t if its velocity when t is equal to 1 is around 12 units per minute. And position when T is 1 is S is equal to 4. So I can say all that symbolically. If A is the acceleration function, and V is the velocity function, and S is the position function, this is telling me that A at any time T is 5, V at 1 is 12, S at 1 is equal to 4, find S at any time T. That's what I have in that big old paragraph. That'd have been quicker to write down, huh? So let's remember our relationship. The velocity is the derivative of the position, and the acceleration is the derivative of the velocity, which is the second derivative of the position. We need to go the other way. We need to start with this, which is the derivative of the velocity, and get the velocity. And once we have the velocity at any time t, we need to peel off a derivative and get the position. You peel off a derivative each time with an antiderivative. So what this is telling me is that my velocity is going to be the antiderivative of 5 as a function of t. So what's the general form for the velocity function? Just 5t, right? Plus the constant of integration. So velocity at any time t is 5t plus c. This is going to help me find c. Its velocity when t is equal to 1 is 12. Use that piece of information to find this constant of integration. So v of 1 is 12. Now we let t equal 1. And we have v of 1, which is 12, is equal to 5 times 1 plus c. So if 12 is 5 plus c, then that makes c equal to 7. And that gives us our velocity at any time t to be this 5t plus 7. Now we do it again. I want the position at any time t. Position is the antiderivative of the velocity. I got to peel off that derivative with an antiderivative. So next, s at any time t is going to be the integral of the velocity at time t. We just found the velocity to be 5t plus 7. So here's where you take over. What do you get when you integrate 5t? Okay, and then the 7? T, and then the constant of integration. We got to find this constant of integration because we know the position when time is 1 is 4. So again, let's let t equal 1. So that my position is 4, and when t is 1, I have 5 halves times 1 squared plus 7 times 1 plus c. So 5 halves plus 7 is plus c is equal to 4. Let's see, 5 halves plus 14 halves is 19 halves. This 4 over here is 8 halves. So I'm going to subtract that to get the c by itself. So 8 halves minus 19 halves is equal to that c. I think that's a negative 11 halves. And go back and put that into the position function right here, where the c is. The position at any time t will be 5 halves t squared plus 7t minus 11 halves. Oh, well, you're all here, you can see it. Okay. Did that make you think of anything that you may have seen on your web work assignment that you want to ask about? Haven't touched it yet, huh? Okay, I wanted to show you today where this notation comes from, where this little integral sign comes from, and this thing with the dx in there. So I said I was going to probably jump to section 5 before I did this, but I lied. I don't want to have to change my review sheet for your test, which is, by the way, 1 week from today. Agreed? So I'm going to talk about section 5.2, which is essentially same as section 5.3, where how this area under a curve has some relationship to the notation that we're putting here. So I'm going to kind of put section 5.2 and 5.3 together. You think of area as the limit of a sum. So I want you to draw me the line. Y is equal to x plus 1. And I want you to see if you can figure out, find the exact area between this graph and the x-axis. From the vertical line, x is -1, to the vertical line, x is 4. First, I want you to draw me the graph. That's just a straight line. Slope of 1, and my y-intercept is 1, and my x-intercept is -1. So it goes through -1, 0. It goes through 1, 0. I'm sorry, 0, 1. And then when x is 4, y is going to be 5. So it looks something like this. This makes a triangle. So we don't need any calculus. You can find the area of that triangle using your geometry. Area is 1/2 base times height. So let's see, this is the point 40. I need you to figure out how long this is and how tall that is. Got it figured? How long is it this way? That's 5 units that way. That's clearly 5 units that way. So the area, I won't write it in there, area is 1/2 base times height is 1/2 of 5 times 5 is 25 divided by 2. Well, what if we had a curve instead of a triangle? What about if I had y is equal to x squared? Say we do that from x is 0 to x is 2. I want to see if I can make this problem that easy. Well, I can mimic this problem. I could say, well, instead of using y is equal to x squared, let's use y is equal to x and find the area of that triangle. Well, then that's kind of stupid because you see I'm off by this much right here. So that's not a great idea, but it's easy enough to do. I can approximate the area under the curve by making that the area of a triangle. But I want to even be more general. What if I had just a random function and I want to find the area under that curve? Well, then I can't find a nice line that fits it so nice and easy. Make triangles out of it. So I make the easiest thing that I can make and find area of, and that's rectangles. I can find the area of a rectangle really, really easily. I can take this region up here, and for instance, I can subdivide the interval from 0 to 2 the way I did here into 2 equal lengths, and then find the area of a couple of rectangles. Like here's a rectangle, and then maybe here's a rectangle. It's the area of this rectangle. Let's see, I have to find out what the value is here when x is 1. And when x is 1, y is 1. And here when x is 2, y is 4. And then I can say the area of this one rectangle here is base times height. So let's call that rectangle number 1, and this one rectangle number 2. So that the total area is the area of rectangle 1 plus rectangle 2. And so the way I've colored it in, I used f of 1 to be the height, and my base width is 1. So it's base times height. And then when I move over to the next rectangle, the height is given by f of 2. My base is still 1, so I take base times height, which is 4. And so that I get that this area, I'm going to put squiggly lines, because that's not the exact area under the curve. The area given by this picture then says it's 1 plus 4, or roughly equal to 5 units. But you can see that's clearly too much area. I've used big old rectangles like that, and I got way too much area. So what I'm going to do instead is put fewer rectangles in there. So let me move the picture over. I want you to remember these numbers, and then we'll come back to it. So let's look at this picture. Y is equal to x squared, and that's 2, and that's 0.24, and that's 1. So that was the 0.11. I double the number of rectangles that I put in there. Cut this in half, and so that this is at a half, and this is at 3 halves. And now let's make some rectangles again. Let's always use the right end point to determine the height, just to make it easier to draw. So there's a rectangle that's just a little bit over. There's one that's a little bit over. There's one that's a little bit over, and there's one that's quite a bit over. So now I have 4 rectangles. And I want to see what the area of those 4 rectangles is. So I do them. I need to get the heights at each of these endpoints. And this function is f of x is x squared. So I'm going to put these numbers in, square them to get the height of each of those boxes. The width of each box is the same. I made them all a half unit wide. So I'm going to take the width times the height. The width is our length along the x-axis, and the height is the value of f at the right endpoint. So the width is the same, so I'm going to factor it all out at the end. And I'm going to say that this area is roughly equal to f of 1/2 plus f of 1 plus f of 3/2 plus f of 2, and then I'm going to factor out the width. They all have the same width. So f of 1/2 is a half squared. F of 1 is 1 squared, and 3/2 squared, since that's my function. So I've got 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared. And then the width of each rectangle is also a half. Let me do the dirty work. That's 1/4 plus 1 plus 9/4 plus 4 times a half. So I have 9/4 plus 1 is 10/4. 10/4 is 5/2. Plus 2/2 is 7/2. Plus 8/2 is 15/2. And write that down before I forget it, times a half. So this says that the area is roughly equal to 15/4. Which one do you think is closer to the actual area? Maybe the 15/4, but they're both overestimates. So why not use the left-hand endpoint instead of the right-hand endpoint, since it's an increasing function? So let me do that. These are both examples of right sums. I use the right-hand endpoint of each rectangle to generate the height of the particular rectangle. In a left sum, I'm going to use the left-hand endpoint. So here's that same graph. Y is equal to x squared. Here's x is 2, so this is the ordered pair 2, 4 again. I'm going to use 4 rectangles. But I'm going to make the height of each rectangle correspond to the left-hand endpoint. So here, my left-hand endpoint touches the origin. So that's really a height of 0. And this one is going to be a height of f of 1, I'm sorry, f of 1/2, then f of 1, and then f of 3/2. So I still have 4 rectangles. My first one just doesn't have any height. So this left sum gives me f of 0 plus f of 1, I'm sorry, plus f of 1/2, plus f of 1, plus f of 3/2, and all of them times that fixed width of delta x. Where f of 0 is 0 squared. 1/2 squared was 1/4. 1 squared was 1. 3/2 squared is 9/4. And the delta x is 1/2. So this particular left sum gives me 10/4, which we said was 5/2, plus 2/2 is 7/2. Multiplied by that is 7/4. There's quite a big jump between 7/4 and 15/4. But my bet is that the actual area is some number in between there. And have to be halfway between there, but it's some number between there because this one's an underestimate and this one's an overestimate. What do you think we do to get closer to the actual area? You can average them. That's a pretty good idea. You can average these two. That's not a bad idea at all. But what I'm going to do is just put more rectangles in there. I'm going to keep putting a bunch of rectangles underneath the graph so that you won't be able to tell after a while where one rectangle ends and the other begins. If I put more and more and more rectangles in here, I should get closer to the actual area. So here's my plan. I'm going to take this, I've got 4 rectangles now. So here's what it looks like when I had 4. Now I'm going to put 8 rectangles in there. I'll put here, 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 and here. So if I take the interval from 0 to 2 and cut it into 8 equal parts, do you agree that the length of each x, delta x here is 1/4? Two is the right endpoint, 0 is the left endpoint, and I said I'm going to make 8 equal-sized rectangles. So delta x has a length of 1/4. So this is 1/4. 1/4 plus 1/4 is 1/2, then 3/4. 1 and 1/4 is 5/4. 6/4 is the same as 3/2, and then 7/4. For the right-hand sum, I plug those right endpoints in and make my rectangles look like that. Now they don't hang over as much. I should get a better estimate. Then I can look at what the left-hand sum looks like, and then do what you said and take an average of the two. Let's go ahead and do the dirty work of finding the right sum over here with 8 rectangles. So I need to find the value of my function x squared at each of the right endpoints. So 1/2, I'm sorry, 1/4, 1/2, 3/4, the numbers on the right side of each subinterval. So my right sum gives me my areas f of 1/4 plus f of 1/2 plus f at 3/4 plus f at 1 plus f at 5/4 plus f at 3/2 plus f at 7/4 plus f at 2. Those are all the heights. Height. I got 8 of them. And then I'm going to multiply by the width of delta x. So let me take those, plug them in here. So that means I'm going to square all of those. 1/4 squared is 1/16. Half squared is a 4. 3/4 squared is 9/16. 1 squared is 1. 5/4 squared is 25/16. 3/2 squared is 9/4. 7/4 squared is 49/16. And 2 squared is 4. And then delta x we said was 1/4. Yep, I got 8 numbers there. Let me get a common denominator of 16. So there's a 1. That's going to be 4. That's 9. That 1 becomes 16/16. And I have 25. 4 times 9 is 36. 49. 4 times 16 is 64. Then I multiply that. All right, let's make yourselves useful. 64 plus 16 is 80. 80 plus 50 is 130. 130 plus 40 is 170. 170 plus 25 is 195. 195 plus 9 is 204. So you 204/16 times 1/4. Let's see, 4 goes into that 51 times. So this one tells me my area is close to 51/16. Let's see, 25/4 is 3 3/4. 51/16 is 48 and 3/16. 7/4 is 1 3/4. So the last couple of numbers I called out were closer to 3-ish, right? What would the left sum look like with those 8 rectangles? What would it be? What would be done differently?
You would add an F0 and not F2.
That's right. All these numbers, take out the F(2) and put in the F(0). So let's do that. So our left sum that's right. What's F(0) in our picture again? 0. So we're really only taking out this last number. All times delta x. So this one's equal to, what did I say this one number was? 204/16. We take away the 64. 140/16. That sound like that should be right? I just took off that last number, which was 4. And F(0) was just 0. So I took out the 4, and that gives me, I lost my number here, 140/16 times 1/4. 1/4 goes into that. Let's see, 3 times 4 is 12. Leave me 20. 4 times 5 is 20. So we get 35/16. So that's 2 times 16 is 32. So it's 2 3/8. So if I'm a betting person, I would say my area is somewhere between this one and that one. If you average them, what do you get? You get 86 over 32. I don't know how big 86 over 32 is. 3-ish. Okay, now I'm going to do this again and again and again and again and again. But I'm not going to do it one at a time. I'm going to do it symbolically. And I'm going to let the number of rectangles become infinitely large, which makes the base width of each rectangle become infinitely thin. So that eventually I'm filling this up with rectangles with such a thin base that really I'm just drawing adjacent line segments and adding all those heights together, because my base width is essentially going to be pinprick size, right? So the heights are just going to be the values of all the F's in there, and I'm going to add them all up. So when we do this in general, it looks like this for this particular function. My right sum is 0. I move over delta x units, so this is delta x. I move over another delta x, so this is 2 times delta x. I keep moving over another delta x until I finally hit x is 2. Then I draw my rectangles to hit the curve. So these are real close together. And then I find the value of f at each of those delta x's, where delta x is going to be the length of the interval divided by some variable. I'm going to put n rectangles in here. So delta x is just 2 over n in this example. 2 being the length of the interval, n being the number of rectangles. I'm going to have n of these in here, where my first one occurs at delta x, which is 2 over n. So this would be 4 over n. 2 times 3 is 6 over n. Until I'm out here at the kth rectangle, it'll occur on the x coordinate of 2k over n. And so what I do to make my right sum is I start with f of 2 over n, then I add f of 4 over n, until I get out to f of 2k over n, and then I keep going until I'm finally at f of 2. And then I take all of that and I multiply by delta x, which is just 2 over n. F in this example was x squared. So for instance, this looks like 2k over n squared. Delta x was 2 over n. I'm going to write this in summation form. Here's our symbol that says add stuff up that looks like that. That's the Greek capital letter sigma. K is going to be my counter. I start from k is equal to 1 and I go to n. And now I'm going to make this go on forever. So I'm going to put a limit out here as n goes to infinity. There are ways to compute that using a known formula. But I want to show you what the transition looks like. This is just some sort of x that's moving along in the function. So this is my f at my special x. Here, my special x occurred at the right endpoint. So here, I'm just going to say some special x at the kth endpoint. Could have been the left endpoint. Could even be somewhere in the middle. This number out here was our delta x. And then this thing is my summation symbol. And then I make the number of rectangles go to infinity. This is something called a Riemann sum. Eventually, I'll show you how to compute these things using some known formulas. But right now, I just want to show you that remember when we came up with the derivative, we took a limit as the change in y divided by the change in x. And that limit was over the change in x going to 0. Well, letting the number of rectangles go to infinity does indeed make the change of x go to 0. 2 divided by infinity is 0. So this limit also produces one of our formulas. When I take the limit of this sum, this summation symbol is what we now write as the integral sign. This is my function that varying over the entire interval, and this becomes the dx. We compute an antiderivative to compute an area, but our antiderivative is a function. So what we're going to do is we're going to take that function and we're going to find its values at the left end point and the right end point, and this limit gives us the exact area. So let's go in general, go from A to B. And so this gives us the area we need. Y is equal to f of x above the x-axis from x is equal to A to x is equal to B. So that's where that funny S came from. It came from making a sum, an infinite sum. And just like before, when we took the derivative, the delta x becomes a dx when that becomes infinite. And then we do this in general instead of point by point. So in our example, the last one that we did, we were finding the area under the curve of y is equal to x squared from x is 0 to x is 2. So in this example, what this is telling me is that my area should have something to do with the antiderivative of x squared from x is 0 to x is 2. Well, what's the antiderivative of x squared? 1/3 x cubed. Now I'm going to draw a bar out here, put my 0 and 2 in there. When I put the 2 in for x, I have 1/3 of 2 cubed. When I put the 0 in there, I have 1/3 of 0 cubed. And we're going to subtract those two numbers, right end point value minus left end point value. And so the exact area under that particular curve was 8/3, which is 2 and 2/3. So I was getting closer, but not very fast. And you probably don't believe it, so that's why I'm going to go back to that first example that we did with the line y is equal to x plus 1, because we found the exact area there since it was a triangle. I want to show you how if you integrate x plus 1 dx, and then put in the -1 and the 4 into your antiderivative and subtract, you're going to get that exact area that we got. So that way this would be more believable that the area is exactly 8/3. So here's our first example again. I'm going to compute the antiderivative of x plus 1. And the x's on the left was x is 1, -1, and the x on the right was 4. And I think we got something like 25. What area did we get on the first example? 25 halves, 5 by 5, work out the back. Okay, so let's integrate x plus 1. What do you get when you take the antiderivative of x? X squared over 2, right? What about the 1? X. Now, I don't need the plus c because we're going to be subtracting. So if I had a plus c here and a plus c there, it subtracts out. Now I'm going to take that and I'm going to put the 4 in for each x. Then I'm going to put the -1 in for each x and then subtract. So 4 squared over 2 plus 4. Then I subtract -1 squared over 2 plus -1. So that's 16 halves is 8. 8 plus 4 is 12. That's going to be 1/2 plus a -1 is a -1/2. So that's 12 1/2. 12.5 is indeed 25 halves. So there it is, there's that exact area. So by gosh, by golly, you better believe that that's the exact area under the graph of y is equal to x squared. And when I put numbers on the integral sign like this, we have something called the definite integral of f with respect to x over the interval from a to b. And if f is a positive curve, then this can be interpreted as the area underneath the curve. And that's where the funny integral sign comes from. The dx comes from the fact that we've got height times width of each rectangle. Height times width. So we'll spend the next day in class talking about properties of the definite integral. And maybe then I'll compute one of these limits exactly for you using some algebra. And then that'll be as far as your test will go. I think that takes us, this part that I'm going to talk about in class next time will be section 5.4. So I'm going to take your test through section 5.4. Sounded good to you? Yeah. And you see how my other class is dying to get in here. We better let them in. Oh, beautiful. Beautiful. Thank you. Thank you. Bye. Have a good day. Bye. No trip. Thank you. Thank you. No. No.
I should that one.
Okay.
67.
No, I got 10 minutes.